the underwater rover with T11. It's Daniel Martinez, Charles English, and I'm Ryan Wright. What it is it's a remotely operated sub that is going to be tethered, non-autonomous, so it's going to have operator feedback to go and control everything, and it's being designed to perform various tasks outlined in the made ROV competition. The date for the competition is still to be determined in 2015, but it usually falls around June. There's three primary tasks affiliated with the made ROV competition, which are shipwrecks, some sort of a science-related task as far as collecting biological samples and swapping sensors, and also conservation efforts are one of the primary concerns. Our main focus is the design considerations. There's a dimensional constraint of 75 centimeters by 75 centimeters. Also keeping it man portable so one person can operate it and launch it. Mobility is one of our primary factors. We're doing drag analysis based on external fluid flow. Also operational depth is one of the considerations since it's going to be taking on atmospheric pressures. Material selection is going to play a critical role in controlling buoyancy, keeping it man portable, and adding to the strength and resistance of corrosion. We're trying to achieve relatively neutral buoyancy just to reduce the amount of operating between the vertical thrusters. And we're trying to keep this cost effective and modular so we can make hardware additions to it and software changes to make it more applicable to various industries. This is our initial design. We have two vertical thrusters, two horizontal thrusters that will now allow to drive kind of like a tanker full track operating system, so it can rotate about the vertical axis and the horizontal axis. We have a gripper assembly on this one, which is one of the requirements for the main competition. And we have two pressure vessels, one for the camera to see where it's going, and the other one for all the primary electronics.
Okay, to give you an idea of the dimensions of our initial design, the overall length is about 18.27 inches, and in the front, the cross section 11.5 width by 8.5 height. And that meets the requirements of the competition, less than about 75 centimeters by 75 centimeters, which is about 29.5 inches. And that requirement is so that the ROV can maneuver into a wreck if needed. Here's a system block diagram for our initial design. We have top side 48-volt DC power supply and a workstation, which is a laptop running our control software. That is going to be tethered to the ROV. Here are all the onboard systems. We have onboard voltage conversion and power distribution. Microcontroller hooked up to electronic speed controller is going to drive the brushless DC motors from the thrusters. We have our cameras going to be connected directly to the laptop. We have a sensor array. It's going to be providing input to the microcontroller back to the laptop, and we'll be controlling a gripper servo. So some of our initial analysis, in designing this ROV, this vehicle to travel through the water, we need to understand the drag forces in play in order to decide what motors and props we're going to be using to push the vehicle. So for our design geometry, it's a blunt body. Drag pressure is going to dominate over friction drag. So we use this function, and we calculated the drag force as a function of velocity. So as you can see, it's an exponential increase of drag force. So we're looking at keeping the velocity low between 2 to 3 meters per second in order to minimize the drag force. In addition, we did fluid flow simulations, velocity of 3 meters per second, horizontal travel. By hand calculation, we came up with a value of 133.83 newtons. SolidWorks simulation was very close at 134.37 newtons. And the ANSYS simulation came out slightly higher, about 13% higher, 151.9 newtons. We plan on revisiting that simulation in order to verify the results.
Our next steps in our design project, as you see, we need to go back and revisit our ANSYS simulations to double check on those numbers. We have to check our thrust propeller calculations as well as selection of our brushing motors. We also have to check our vessel for the pressure depth. The main competition depth, since it's in a pool, it's going to be about 30 feet, but our personal goal as a team is to get to 100. That's the average, like scuba diving, where we can go in and check wrecks and coral reef growth and progression of such. We also have to allow, our vessel allows for modification and growth as in software, so we can attach more components and be able to easily expand. This is a quick cost analysis of our project. We have our time estimates as far as different aspects of the team. We projected our labor cost to be about $30 per hour, and then on our right is our materials cost. And our total is, as of now, is $197. The asterisk, the notes are expected costs because we have yet to reach that step. This is our quick timeline from the beginning of the year through the end of 2014. Beyond our competition, our main goal, our ROV can ocean survey as far as ocean platform, oil platforms, and inspect tunnels and pipelines and cables and such. Also can ocean cleanup with our use of the gripper. We can pick up debris and anything that is causing hazard to the environment and remove it from the area. There's also search and rescue. With search and rescue, some ROVs were used in the Malaysian aircraft searching at the depths of the water. And so these are some of the manufacturers who also manufacture ROVs and some of the university projects. This is our final goal. Resources and our images. Any questions?
Are you going to build one of these?
Yes, sir.
Okay, because you say design a remotely, it really should say design and build a remotely controlled vessel. If I'm reading that correctly.
Yeah.
That's an oversight.
And are you going to test it in locally down in the reefs somewhere, or in
We're gonna start out with testing the pools, and from there probably move to like an intercoastal location. I know where I live, William Reef is approximately 30 feet deep, and it's at high tide, it has crystal clear water, so it's for a saltwater condition, probably one of the better scenarios. And from there, possibly seek out certain areas to try to push it into the ocean and try to actually hit that 100-foot goal.
Okay. Your basic design, buoyancy, is it designed to have a negative buoyancy? Is it designed?
We're trying to design for a neutral buoyancy to go and reduce the operating of the vertical thrusters.
In freshwater or in saltwater?
Well, it's going to have a system, with it being modular, we're going to account for being able to add counterweights to it to help make it more neutral for, like, to trim out the buoyancy.
In addition, as you go up and down in the column of water, your neutral buoyancy has been changed somewhat. So the design, as you can see, is slightly, the frame, there's lots of points where we can have buoyancy or weight in order to, once you determine your operating envelope and where you're operating, you can change your buoyancy so that it's neutrally buoyant in that envelope.
Okay. Second question, fouling. What are you doing to compensate? I see the 4 tubes, but if I put this on the bottom and I turn that motor in the wrong direction, I'm going to suck the sediment right through my.
Not shown in the diagram from the initial design, but there's going to be grading or some sort of on the ducts to prevent anything.
And then the third and last question, and I use that nice coral reef that you've got there. What safety bailout are you going to create into it that will protect you from locking that into some structure like a coral reef down at the base? If you get hung up, you've got a tether on this thing.
Being that it's remotely operated, that's going to be dependent on the operator. So they're going to have to evaluate the situation, make sure that they don't get into anything that's going to have too critical of an overhead or anything like that. They can cause snagging of the tether. And that's all dependent on the operator, making sure that they're cautious to their surroundings.
I was hoping like that arm that you're putting on there could be used to physically move yourself up off the bottom so you have the ability to do something.
Part of the reason for the arm, we decided to go with a stationary arm and have the 2 vertical thrusters to pitch the ROV, was to reduce costs, so that way we wouldn't have to deal with waterproofing servos for going and pitching the entire arm, and also to eliminate having to pan or tilt the camera. That'll keep everything in a set frame rate and to reduce moving parts to help minimize failure points.
Okay.
Do we have more questions? No?
All right.